March the 16th, and this is Nighttime Mathematics Radio. Well, it's a shut-in world, but the math homework hasn't stopped, so if you need any help, feel free to tweet over to @NightMathRadio on Twitter, and I'll try to help you right here on YouTube. So we'll take a quick break at the beginning of the program here to see if anybody has any questions they want to tweet in. And if not, we'll go on with the questions that got asked over the week. Got some questions about related rates and some questions about optimization and differential calculus. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio, the show where you tweet your questions to me here on Twitter, and I'll answer them live on YouTube. So over the course of the week, we got a couple of questions about optimization and about related rates in calculus. So one of these questions is something of a chestnut, except whenever math books try to use it, they know it is a chestnut, so I always try to mix it up just a little bit. And so here's the question we got posed. We're told a farmer wants to and let me switch over to the notepad so we can see what we're talking about here. We're told the farmer wants to fence in an area of 1,500,000 square feet. So we have an area of 1,500,000 square feet. And I'm cheating slightly here using the metric feet squared. It's traditional in imperial units to use SQ space FT space, but I just can't be bothered because that's silly. They want to fence this in with a rectangular field, then divide it in half with a fence parallel to one of the sides of the rectangle. So we're making our usual rectangle here. With length L and width W, except now we're splitting it with another fence here in the middle. And what we're asked is, what are the dimensions of the rectangular field that minimize the cost of the fence? And we're assuming that the fence costs proportional to the actual length of fence that you've got. So what do we know here? Well, we know the obvious, that the area is equal to the length times the width. And now, we know up here that the area is 1,500,000 square feet. I'm just going to call it A for most of this problem. Why? Because it really doesn't help us to write 1500000 over and over and over again in every line of this problem. We could do it if we have to, but this is what variables are for. Let's call it A. I can write A much more quickly than I can write 1,500,000, and I'm much less likely to get something wrong. So let's write it like this. And what we're trying to minimize is the total length of fencing, which is, well, I see 3 lengths and 2 widths. And that's one way this problem varies from the usual chestnut. The chestnut version of this problem is you just say, well, you're fencing in a field in a with a rectangular bit of fence. So you say, well, in this case, the cost is just the perimeter, 2L plus 2W. But that's not what we have here. This time we've got a 3rd length, and we have to pay attention to it. Okay, this is great, but this looks like a mess. After all, we all signed up for a single variable calculus class. This is multiple variables, but we can get rid of one of them. Because after all, we know the area is length times the width, so I could just substitute one of them out. I could say, for example, that the width is equal to the area divided by the length. And that way, I can get rid of the width. I can eliminate it by substitution. 2 area over length. Now I've gotten rid of it with substitution, so I don't have to think about it anymore. It's all in, everything I've got here is now either capital L, the thing I'm trying to minimize, lowercase l, which is the length, which is the thing I'm changing, and the area, which is just a constant. The area is some number. I'm just calling it a because I don't want to think about it. A is not a function of length. A is not a function of width. A is not a function of L. A is just A. We know what it is. It's 1,500,000 square feet. We just didn't feel like writing that over and over again. So when we go to do calculus, let's remember this thing isn't actually a variable. We don't have to take derivatives of it with respect to things. I mean, we could, but it'll be 0, so who cares? So let's take the derivative of L with respect to the length. Well, that's 3 plus twice the area times the derivative of 1 over L, which is minus 1 over L squared. So what I have here is the lowercase l, is equal to 3 minus 2a over L squared. And remember, I want to know where the turning point is. I can see, for example, that when L is, let's see, because remember, looking back at the original formula, I can see that when L is very, 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 very small, this is enormous! Because if L is tiny, so my field looks like some ridiculous thing. If my 1,500,000 acres is stored in a field that's 1,500,000 square feet is stored in a giant field that's 1 foot in length and 1,500,000 feet long, I'm spending a lot of money on fencing here. Because that's, just in these 2 things, that's 3 million feet worth of fence. Ugh, that's too expensive. On the other hand, if I make L really, really big, again, my cost is going to be enormous. This will be small, but now I'm spending it again. Now I'm spending even more. So I make the field this way, say, a foot wide and 1,500,000 feet long. Remember, I divided it in half along that direction. Now I'm not spending, now I don't have 3 million feet worth of fence. I have 4,500,000 feet worth of fence. That's ridiculous. We're not doing that. But somewhere in the middle, there must be a minimum. And that's what we're trying to find. And again, the usual way you do this in differential calculus is you take the derivative and set it equal to 0. And now we can just solve for that. So we say, okay, I'll add 2a over L squared to both sides. So 3 is equal to 2a over L squared. I don't feel like having fractions, so I'll multiply both sides by L squared. L is a nice, well-behaved length, so it's not 0. There's nothing funny happening here. So 3L squared is equal to 2a. L squared is equal to 2a over 3. L is equal to the square root of 2a over 3. Does that work? Well, sure. A is an area, so it has units of length squared. We take 2/3 of that and square root it. Bob's your uncle, you're done. What is that? Well, remember, the area was 1,500,000 square feet, so twice the area is 3 million square feet. Divide that by 3, we have 1 million square feet. So this L is the square root of 1 million square feet. That's 1,000 feet. And now we're in good shape. Because if L is 1,000 feet, and L times W is 1,500,000 feet, W must be 1,500 feet. And we're done. This is a classic kind of problem. You see these all the time. Because after all, we have two terms here. You can see we're trying to find a sweet spot. If we make the length too big, you spend a fortune on fencing. You make the width too big, you spend a fortune on fencing. Somewhere in the middle, there's got to be a place you're spending less. And that's here. So before we had millions and millions of feet of fencing. This time we have 3 times the length. We have 3,000 feet here. Another 3,000 feet there. So this time it's only 6,000 feet of fencing. That's a lot cheaper. This is Nighttime Mathematics Radio. Let's take another break to let people tweet in any math questions they might have. We'll be back in about 2 minutes. This is Nighttime Mathematics Radio. Welcome back, nation of shut-in math students. This is Nighttime Mathematics Radio. Coming to you live from our secret base by the bay to bring you the best math help we can to a world with no schools but a ton of homework. Let's look at the second question that got asked over the break. This time we're told two people are standing 50 feet apart. I'm going to assume they're a straight east-west direction. Here's one person. Here's another. They're 50 feet apart here. Then one person starts walking north at a rate, so the angle shown here, they're taking off to the north, such that this angle theta is increasing at a constant rate of 0.01 radians per minute. So we're told d theta dt is 0.01 radians per minute. And notice when you're writing units, it's traditional to put R in a little bit of parentheses. The reason is, remember, radians are unitless. Radians are defined to be arc length divided by the radius. And since that's a length divided by a length, radians don't really have a unit. But it sometimes helps to remember that you're thinking about radians. So you sometimes put the R in parentheses like this. Say, well, it's radians, but that's not really a unit. So we'll just leave little parentheses there. Then what we're asked is, at what rate is the distance between the two people changing when theta is equal to 0.5 radians? So what's the rate at which the distance d is changing? Well, let's take a look. This speed is funny. This is lowercase d here. That's the thing that's actually changing. That's the direction he's going. Let's actually not call it lowercase d. Let's call it lowercase l just to not have dd, because dt just hurts your head. Let's not do that. Call it lowercase l. So what do you know here? Well, d is the hypotenuse of a triangle, so d squared is equal to 50 feet squared plus L squared. So that's the thing. What we want to know is, what's d capital D dt? Well, let's take a look. Let's solve for d. D is equal to the square root of 50 feet quantity squared plus L squared. So dd dt is equal to 1 over the square root of 50 feet quantity squared plus L squared times, well, derivative of what's inside, chain rule, 2L. And actually it's 1 over 2 this, because that's one, this is the 1/2 power, times twice the length, times dl dt. Well, that's great, you might say, but I don't know L, and I don't know dl dt. But we do, because what we want is theta, not lowercase, not L. But remember, we know tangent L, tangent theta. Tan theta is equal to L over 50 feet. Opposite over adjacent. So I can substitute in this. I can say, okay, so dd dt is equal to 1 over twice the square root of 50 feet squared plus 50 feet times tangent theta squared. That we know. We know tan theta because we know theta is 0.5 radians. And we have a calculator. We've got a 50 feet squared on both terms, which is we can just factor it right out of the square root. Times twice the length. Well, the length is times 50 feet times 2 times 2 times 50 feet. Honestly, I should have just canceled the 2's, but I'll do it right now. Times tan theta times the L dt. Well, that's 50 feet, because L is 50 feet times tan theta. That's 50 feet secant squared theta d theta dt. This is a mess. Let's simplify some of this, huh? The 2's cancel. I could factor the 50 feet out of each of the two terms here. It's 50 feet squared in each term, so that's 1 over 50 feet squared times things, which is, I factor it right out, as 50 feet, times the square root of 1 plus tangent squared theta, times 50 feet, times tan theta, times 50 feet, times secant squared theta, d theta dt. The 50 feet here cancel. That makes things even easier. And now we've got something interesting. Tan theta, remember, is, in terms of the coordinates on the unit circle, that's just y over x. That's sine over cosine. So this is sine squared over cosine plus cosine squared over cosine squared. So that gives us sine squared plus cosine squared in the numerator over cosine squared in the denominator. Sine squared plus cosine squared is just 1. So that's 1 over cosine squared, better known as secant squared. This is a trig identity you might have forgotten, but it's easy enough to work out in the field. So that's 1 over secant theta times tan theta times 50 feet. Still up there, I'll bring it up. Times secant squared theta times d theta dt. One of our secants cancels. So this gives us something kind of nice. We now have d dt is equal to 50 feet. Now times tangent theta times secant theta. That's just sine theta over cosine squared theta. There's nothing particularly nice there. I mean, we could rewrite it a bit if we want, but that's all right. Tan theta, secant theta, d theta dt, but we know d theta dt times 0.01 radians per minute. And this is now all very easy, because we know theta, it's 0.5 radians. We know tangent is 0.5 radians, we can plug it into a calculator. We know secant of 0.5 radians, we can plug it into a calculator. So at this point we're done. We're all set for plugging into a calculator and finishing the problem. This, by the way, is why in pre-calc they made you memorize all those trig identities. It's because when you get to a problem like this, the trig identities clean up your mess for you. You've got a 1 plus tangent squared in the denominator in the square root. Well, that's easy enough. 1 plus tangent squared theta is just secant squared theta. That's nice. And it's in the square root, so that just becomes secant theta. That's nicer. This is what pre-calc was all about. And it's hard to explain that at the time, because when you're taking a pre-calc class, students always end up asking, why do we need all this stuff? What is this for? And the answer is, well, the class really is exactly what it says on the tin. This is pre-calculus. It's stuff that will be good to know when you get to calculus, as we just saw. This is Nighttime Mathematics Radio. Okay, let's take one last pause to see if anyone has any last questions on Twitter. If they do, we'll answer them there. If not, we'll probably call time off and come back tomorrow. This is Nighttime Mathematics Radio. Okay, everybody, that looks like we've got all the questions for tonight. This has been Nighttime Mathematics Radio. Remember, this is where you can stop by, ask your math questions, get them answered live on YouTube. Good night, everybody. Stay safe. Good luck with your homework in the absence of school. See everybody tomorrow night.